Who we're lucky he happens to be in Montreal also because he was attending the cognitive science meeting.
Well, the cognitive science meeting is coming up. I was at the mathematical psychology.
The mathematical psychology, and then the cognitive science meeting.
Well, I'm actually, I'm not attending that meeting, but yeah, that's happening next.
So there's a meeting happening. He came to the mathematical science psychology meeting, and so he's currently an associate professor at Swansea University in the UK. I heard of his work before, but I only actually met him in person a few months ago at Cardiff at the MEG UK meeting. That's where we got talking, and so how I heard it's going to be in Montreal this summer. And so he has, I believe, he did his PhD in psychology and cognitive science. Yeah. I was in Indiana, and then he did a postdoc in Pennsylvania University, working with Michael Kahana, who's, for those of you who know, is also doing a lot of intracranial EEG recordings and looking at memory in humans. And then he got a position at in the UK University of Swansea, and he's been a visiting scholar also at Pennsylvania. So he's currently spending a few weeks in Pennsylvania, again visiting, and he actually came to Montreal by, I'm not going to tell you the story of his life, but I'm going to tell you that he came from Montreal by train, and he has this very special bike here that he's using to travel around different cities and discover, so it's a nice way to discover the city. And also a disclaimer, we did not agree on what we're going to wear today, so we just wear this just by chance. We're not part of a secret club or anything.
Great minds think alike. Yeah.
Exactly. Yeah. So without any further ado, we're very happy to welcome him for this talk, which is entitled Dynamics of Memory, Decoding Brain Activity with Machine Learning. Do you mind if people ask you questions during the talk, or you prefer to have the questions at the end?
So that's what's the first thing I was going to tell everyone. I'm very happy for you to interrupt me with questions. If anything is unclear at any point, or if you have any questions or comments, feel free to raise your hand or get my attention. It's a relatively small group, so I'm happy to have that. Have the talk be as interactive as you'd like. So please don't be shy. So I'll be giving you a bit of a whirlwind tour of some of my research looking at episodic memory. And in general with memory, we have the issue that lots of things happen before we get any behavior. So a lot of times people like to think of it as as of performance in memory tasks as requiring the successful completion of several quite different cognitive processes. So first of all, when you imagine you're exposed to a new stimulus, you need to encode that stimulus into memory. You need to make sure it gets stored and over the retention interval until you need to access that memory. And then at some point, at an appropriate time, ideally, you're required to retrieve that memory. And if you think of somebody in a memory task where there's a study phase and maybe a test phase, by the time you get behavior, in this task or performance in this task, successful recall, say in a free recall task, requires the successful completion of all of these different processes, and that represents a challenge for understanding these processes because oftentimes deficits or errors in these kind of tests can be explained by the breakdown of any of these different parts that are required for successful memory. And I want to convince you, if you're not already convinced, that looking at ongoing neural activity during these tasks and using these machine learning methods that I'll be describing as well, offers a really great tool for getting a kind of real-time window into cognitive processes as they unfold during memory tasks. And specifically, I'll be talking about two different kinds of memory tasks. I'll start off the talk with the recognition memory task. So this will focus on really the kind of signal that allows us to match a probe item to our memory, and I'll get into a bit more detail of what specifically I mean by that in a moment. And then this is work with healthy individuals who have scalp EEG recordings. I'll explain that in a moment as well. And then the second part of the talk, I'll be speaking about free recall experiments with neurosurgery patients who have electrodes implanted inside their brains, and we can record from those while they're engaged in these tasks. And there we will be trying to look at distinguishing effects that are due to changes in encoding and retrieval processes. So that's a kind of quick overview of the talk. So I told you I'll start off with recognition memory. So the task is, we give people a list of words to study. This is the study phase, and then what I'm showing you here is the test phase. In the test phase, there'll be a probe item on the screen, and the task is just, is this an old item or a new item? And participants are asked to respond old if the probe item matches an item that they were just asked to study, and they're asked to respond new if it's an item that they haven't studied before. And so the question is, what happens between the onset of the probe item and the actual response, or what is the nature of the signal that the evidence signal in this task allows us to distinguish what's old from what's new. When you look at theories of recognition memory, there's often this this divide with where people talk about single versus dual process models of recognition memory. The idea is that intuitively, if you think about what happens when you see something and you're trying to decide whether this is old or new, there's introspectively there's quite different things that happen. And you can imagine, I think maybe most of you will have had that experience where you run into somebody and specifically, exactly that this person, you're 100% sure you've met before, but you have no idea what the name is, how you know this person, or any other bit of context. And so this is often referred to as like the butcher on the bus phenomenon, because it often happens when you encounter somebody who's familiar in an unfamiliar context. In this case, a butcher that you might go to get your meat, and you end up sitting next to that person in the bus. And this would be an example where you have a high degree of familiarity. You have strong sense that you know this person, but you cannot recollect any specific details of previous encounters or anything else that you might associate with that person. Whereas at other times when you run into people that you not only have this sense of familiarity that you've met before, but you also remember specific details of previous encounters or their names, occupation, other details. And you can imagine that all of those things will be reliable signals that allow you to decide that this is actually somebody you know. And so this is a very common distinction in theories of recognition memory, that the idea is that there might be two different kinds of signals that are somewhat independent. This familiarity signal that's quite general and that can occur even without any specific recollections, and then also specific recollections of previous encounters. For example, what you talked about the last time you met this person. And in general, when people looked at trying to distinguish between these types of evidence signals and use, especially when they've used neuroscience methods to look at this, they've concluded that these signals have different types of time courses, and in fact, and specifically, the common assumption is that there's a very quick, early familiarity signal, and then that recollective processes kick in a bit later and come online later in this decision period, and then. And oftentimes then the assumption is that you make an old or new response that could be primarily based either on this familiarity signal or on a recollection signal, depending on whatever happens to be stronger in a particular trial. Okay, And so I'm going to be looking at specifically what happens during this time to try to shed light on the nature of the evidence that allows us to make this all new decision. And as I mentioned before, these experiments are carried out on healthy individuals who have scalp EEG recordings, so just a large high density grid of electrodes all over the scalp. And the way I'll be analyzing these data is I'll take trace like this. You get a voltage trace from every electrode that you're recording from, and I'll decompose that signal into different frequencies. So you can decompose the signal into different frequencies. So this would be the low frequency filter, like this would be the signal filtered at a low frequency. This would be at higher frequencies, and you can basically look at the amplitude or power at each of these frequencies to quantify at each time point how much signal there is in this time series at each given frequency. And so this gives us a bit of a more kind of high resolution signal or description of the signal, as opposed to maybe the more traditional way of analyzing EEG data that's done by averaging lots of trials and getting ventilated potentials. So in this case, we get power signal at each time point for each trial, and can do like trial by trial analysis of these data. And here is it's a power contrast that you get in this experiment. So let me walk you through this figure. So because we have lots of different electrodes, what I've done here is I've just summarized or averaged these kind of frontal electrodes in this left panel and kind of more posterior electrodes in this right panel. So these are regions of interest that are often used in EEG studies of recognition memory. And what I'm showing you here on the x-axis is time. So 0 would be the point where the probe item comes on the screen, and then at the end would be the time when the response is made. And then on the y-axis is frequency. And so in these plots, red color signifies that at this particular time point, at this particular frequencies, more power corresponds with successful recognition, and the blue squares denote that at that particular time point, that particular frequency, less power is associated with successful recognition, performance in that recognition memory test. And the white squares just are combinations of frequency and time points where that contrast does not survive correction for multiple comparisons. And so when you look at this, there's a few things that you can see. There's a rich temporal dynamic, and kind of, when you just look at this, it looks like maybe there's something happening early on and then something quite different happening later in that time series. And you can also see some maybe slightly more subtle differences between frontal and posterior electrodes. So for example, here maybe that kind of red region here extends further to later time points, and this is also something that's often associated with recollection signals in previous studies. So just by looking at this, you might think, oh, maybe there's something to this notion that there's very different types of signals at different times. But it's very hard to know what to make of these contrasts, because we cannot tell whether the signal that we are recording from here is really telling us something that's different from the signal that's recorded earlier on. Even though the contrasts look quite different, it just could be a different way of encoding the same type of information. And so this is really where the power of these machine learning techniques is allow us to quantify the information in the neural signal at any given time point, where that becomes really important. And so just to give you a quick overview, we have lots of electrodes, we have lots of frequencies, we have lots of time points. So this is a very high dimensional problem, because it's very hard to visualize lots of dimensions. I'm just going to show you a two-dimensional view to illustrate what we'll be doing. You can imagine that maybe the x-axis here could correspond to power in one particular frequency at one particular electrode and at one particular time point. And maybe the y-axis is the power at the same frequency, the same time point, but maybe a different electrode, for example. And so this is in this two-dimensional space, you might then plot activity at that time point, at frequency, and electrodes for successful recognition memory trials, so trials where people successfully recognize an item as old as x's, and maybe trials where people or actually, let me walk back. This is actually we're not actually in this case looking at participants' responses. So we're looking at targets versus lures. So in this case, you might show target probes or the neural response to target probes as axis, the neural response to new probes or lure probes as circles. And when you look at this this space and how it's partitioned, you can see that there's considerable overlap between these types of stimulus classes. So it's not so there's not a clear dividing line that separates all targets from all lures. But at the same time, the distribution is also not random. There's some structure in there. And if you were to partition this space, you could predict what probe type the neural response corresponds to with above chance accuracy. And that's exactly what we're trying to do here. So you can imagine that if you apply this type of some classifier on there, that classifier might come up with a partition like this. And so you could then imagine, you could predict that any time neural activity falls into this region here, it's likely that it corresponds to a target. Anytime neural activity falls into that region over here, or maybe down here in this corner, you'd predict that it is associated with the lure. And not only can you do can you make binary predictions like that, but you can also get a sense of how strongly the neural signal supports either a target or lure interpretation of the data by just looking at the distance from these boundaries. So imagine if you had neural activity that falls up in this upper corner here, you'd be quite certain that that would be a target or would correspond to a target. Whereas if you had neural activity that's close to this border here, maybe you'd be a lot less certain. And likewise for neural activity over here on this side, which seems to clearly correspond to a lure, as opposed to neural activity that's much closer here to that border. And in fact, you could interpret the neural activity at any number of different thresholds by just just moving this border around can make it more conservative to make fewer and fewer target predictions, or more liberal to make more and more target predictions, and you would trade off your probability of correctly predicting a target with the probability of falsely predicting a lure item as a target. Okay, and so this is just summarized here. We have 4 different types of trials in this context. We present targets and lures, and we can predict old versus new. So if you have a correct target prediction, we call this a hit. If you have incorrect target prediction, so we say new when the item is actually target, so if we miss the target, we call that a miss. If we say old to an item that's actually lure, we call that a false alarm. And if we say new to a lure, that's a correct rejection. And this is the same partition of trial types that you would get in an experiment when you just look at participants' responses, right? So the participants will also say old versus new, and they're also presented with either target or lure, and so you can classify the responses that people make in this type of experiment in the same way, and to hit false alarms, misses, and correct rejections. So we can analyze the output of the classifier in the same way that we analyze responses of people in this experiment. And in fact, and please, if I'm going too fast or if it's too boring, you can just please do interrupt me. Even though we have 4 different trials and in this 2x2 matrix, really we only have 2 degrees of freedom, because we know exactly how many targets we presented, we know exactly how many lures we presented. When we know the proportion of old responses to targets and the proportion of old responses to lures, we then also know what the proportion of misses and correct rejections is. So we can just calculate those from the hit and false alarms rates, and so really hits and false alarms define performance. And one standard way to analyze performance of individuals or classifiers, in this case, in this context, is to just plot false alarms against hits as a function of different thresholds that, like I've described before. So I'm illustrating this here in this plot. So what I'm showing here on the x-axis is the probability of a false alarm, goes from 0 to 1. Probability of a hit goes from 0 to 1. And if you have a classifier or a person who's completely unable to distinguish old items from new items, the hit and false alarm rate is just a function of your threshold for saying yes. So if you always say old or yes, you get a hit rate of 1 and also a false alarm rate of 1. If you never say yes, you get a hit rate of 0 and a false alarm rate of 0. And if you just flip a coin, if you just randomly say yes or old, then you get a 50% hit rate, but also 50% false alarm rate. So this would those responses for somebody, either a machine learning classifier or a person who has no idea whether a probe item is old or new, we would expect those responses to fall on this main diagonal here. If as I said, so when we start with the most liberal threshold, where we say everything is a target, that would be this point here. We get 100% hit rate. We never miss a target. We always correctly identify all targets as old. But also for all false alarms, we incorrectly classify those as old as well. So we get 100% false alarms. For all lures, we get 100% false alarms. And to the extent that a classifier or a participant in this experiment can distinguish old items from new items, as we make that threshold more and more conservative, as we are less and less likely to classify a probe item as old, we'd expect the false alarms to fall off much quicker than the hit rates. And so we'd expect maybe a strong reduction in false alarm associated with a small reduction in hit rate. And so this might look like something like this. And as we keep going with this, we keep expecting smaller reductions in hit rate to coincide with larger reductions in false alarm rate, and we would expect in that case this to trace out a function that kind of bends upwards away from the main diagonal. And we can connect the dots here, and this is what's commonly known as a receiver operating characteristic function in the context of signal detection theory, for example. And so this is just simply this function, false alarms against hits for different response thresholds. And because the amount of kind of bending away from the main diagonal is a good index of classifier performance, or performance of individuals who try to classify old items and from new items, we can just look at the area under this function as a measure of performance, both for the classifier and for our human participants. And that area measure is 0.5. For the main diagonal, we have a unit square here. If we just take that area under the main diagonal, that would just be 0.5. So 0.5 corresponds to chance performance, and because we have a unit square, the maximum would be a function that goes all the way up to this point here. We never as we reduce the hit rate, we never reduce false alarm rate. So it would be this point, and that would be a area under the ROC function of 1. So that's the scale of the performance measure here that I'm going to be applying to both data from our participants and to the classifier that I'm about to present. And I'll be referring to that measure as AUC, that stands simply for area under the curve, and the curve is this receiver operating characteristic function here. Okay. All right. So how are we building this neural classifier? I gave you this overview of the general idea that we're trying to partition this very high dimensional space to make predictions. But now I want to tell you about what kind of features we use to train this classifier. So one of the challenges in this kind of task is that we never know how long it'll take somebody to make a response to a probe item, right? So we give somebody a probe item and ask them, is this an old item or new item? Sometimes people will be very quick and say, this is old, this is new. Sometimes it will take longer. And so we have lots of trials and we need to align them somehow. And we also want to avoid classifying the actual recognition decision. So what I've done here is, we have the probe item, we have a recognition decision, we also have confidence ratings. I'll talk about that in a moment. So what I've done to avoid any of this actual responding from affecting our neural activity in that for the classifier, I've taken away the last 100 milliseconds of every trial, just the 100 milliseconds before they make a recognition decision, and I'm disregarding that neural activity. And then the rest of the trial, I'm partitioning into 6 equal time bins. And so the length of these time bins varies with the length of the response here. So you can imagine if it takes 700 milliseconds from the probe onset to the recognition decision, we'll chop off the last 100 milliseconds, and then we have 100 milliseconds per bin here. 6 times 100 milliseconds is 600 milliseconds plus 100 milliseconds here is the 700 milliseconds response time. Likewise, if you have 1300 milliseconds, we chop off the last 100 milliseconds, and then in this case, each bin is 200 milliseconds long. Okay, and so this is how I'm aligning the trials here, so that we have kind of like a different neural features for different times in this in this response period. And for each of these periods, I'm looking at power in these in 15 frequencies, from very low to very high frequencies in the signal, like I've described earlier.
Christoph, can I ask
yeah.
a quick question? So, from what I understand, the recognition decision is actually prompted. So you wait for the question, and then it's not as soon as you recognize. So
No, it's as soon as you. All participants see on the screen is they see a probe item, and they're asked to respond. Although new whenever.
As fast as
I'm not. Yeah, I mean, I think. I don't remember if we actually ask them to be as quick as they can in the experiment, but usually participants try to get on with the experiment.
Okay, so what I mean is the recognition decision is the timing of the button press presumably is going to change across trials.
Yes, that's so. So actually,
time zero here is when you say 100 milliseconds before button press, it might not necessarily be 600 milliseconds after the probe.
Right. So that's So well, first of all, I mean, it's a minor detail, but we actually asked participants to verbally respond, yes or no, for is this an old item, and actually we asked them to say pes or po to be able to equate the onset of the first phoneme in the audio recording, so to get an accurate measure of response time here. And yes, so you're completely right. The response time varies from trial to trial, and that's why the length of these bins also varies from trial to trial. So I think the lower threshold was like maybe 300 or so milliseconds. So we always have trials that are longer than 100 milliseconds. But whatever the response time is, if it's 700 milliseconds, I'll take off the last 100 milliseconds. If it's 1300 milliseconds, I'll take off the last 100 milliseconds. And then whatever time is remaining, in the first case maybe 600 milliseconds, in the second case 1200 milliseconds. I'm just using these examples because they're easy to divide by 6, right? But it could be any response time. It could be 1000 milliseconds, 859, or some whatever the response time on a given trial. The remaining time after I chop off the last 100 milliseconds, I just divide into 6 equal time bits. Okay, and so for the first analysis, I told you earlier we were interested in the dynamics here and early versus late signals. But for the first analysis, I just want to quantify how much signal do we have in the data total. And so I'm training classifier on all of these, on data from all of these bins, and just throw this all in the classifier. And I want to compare human performance in this task. Like I've described, we can generate these ROC functions, look at the area under the curve for human participants, and we can do the same thing for the classifier that's trained on all the available data up to 100 milliseconds before the recognition decision, to just get an idea of how much information about the target versus Lewis status of the item is contained in the EEG signal before a response is made. Yeah.
So by doing this, you assume that the process you will be looking at will be exactly the same, even though it's different durations, right?
Yeah. So it's a bit. So I'll, in a little while, I'll show you an alternative way to analyze the data where I keep the length of the time bins constant, right? So it's always because the trials vary, the duration varies from trial to trial. You have to do something to align them, and you can either assume that the time bins, whatever length of time bins you choose, you keep that constant, or you keep the window that you're looking at constant, and then you change the length of the time bins. And I've done both, and I'll show you the other way toward the end of the talk. Yeah. Any other questions? Okay. All right. So here's the results, and let me walk you through from this kind of first comparison. Let me walk you through this figure. So what I'm showing you on the x-axis here is the area under the curve for the confidence rating. So we can, as I said in the previous slide, we collect after the recognition decision. We also collect confidence ratings, and that allows us to analyze the data at these different types of thresholds, because we can look at only the more confident trials, the less confident trials, and so on, to look at the likelihood of making a target decision at these different thresholds and compare that with different thresholds for the classifier. And so this is the area under the curve for these confidence ratings, the binary decision followed by the confidence rating, so the performance in the task by our human participants. And again, it varies from 0.5 here to 1. And we can compare that with the area under the curve for the EG classifier. It's also here just plotted from 0.5 to 0.1. To 1. And there's a couple of things that I want you to take away from this figure. First is that, well, maybe the most obvious feature is here that all of the points are in this lower triangle, and that just means that people are better at distinguishing targets from lures than I'm able to do by just looking at the same people's brain activity, right? And so that's something you'd expect, right? If I'm able to classify targets and lures better than people themselves can just by looking at their brain activity, that would seem quite unlikely, especially given that we have a very crude measure of brain activity. We have just electrodes on the scalp, so we're missing a lot of what's actually going on in the brain when people do these tasks. But nonetheless, even though we're not quite as good as introspection in this task, performance in the EEG classifier is quite high and goes all the way up to AUCs of over 0.8, and importantly the area under the curves are highly correlated. So you see a very strong correspondence here between the area under the curve that we get by just looking at people's responses, no neural activities involved in the calculation of these, or by just looking at people's neural activity before they make any responses, so no actual responses involved in calculating these. Yeah.
Is it average across time beams and sensors? Or?
So this is for classifiers that get all time bins, but they're not average. They get 6 different features for each trials for each frequency.
So you gave all the time beams at the same time to the
Yes. Yeah. And I'll show you some other analysis where I don't do that in a moment. Yeah.
So the labels that you have for this classifier and that classifier, they're not the same, right?
No, they are the same. In both cases, well, this is not a classifier, right? So I ask people, is this a target or lure?
Right. So the targets and the lures there is the answer of the participants, but the AUC that you get for your EEG classifier is how well it identifies the true labels, not the participants' answer.
Well, this is how good participants identify the true label. This is how good the classifier identifies the true label. Right. So in both cases, here I'm asking
exactly. So I'm saying it's the true labels. So it's not the how well it detects the answer of the participant.
Yes, it's always.
You could have run the same EEG classifier to see whether it detects. It might be better at detecting the participants' response.
Yes.
Right.
No. Yeah, that's right.
Then it follows its behavior. Because if you're looking for similarity, it might be closer to.
Yes, no, that's true, and that's an important point. The thing is, in this case, performance was quite high, so I would expect the results to be quite similar in this case. Most people, these were highly motivated subjects, and if you look at the AUC here, there's almost all of the AUCs are above 0.8, so performance in this task is very high. But if we just wanted to, for example, if you just wanted to rank order people and in their ability to distinguish old from new items, if we did this with just based on the brain activity, not looking at any of their responses, we would get very similar results than if we actually looked at their responses. So that's encouraging. That tells us that there's quite a bit of signal in the EG activity here, and that whatever signal we're picking up with the classifier is likely to be related to whatever signal participants use when they make their old new decisions. Okay. So as I mentioned, we are interested in the dynamics of this task and trying to understand what types of evidence might be available to people, and and particularly if there might be different types of evidence that become relevant at different times during the recognition decision. And so what I'm doing now to look at this question is I'm going to be training quite a number of different classifiers on different partitions of the recognition decision. So I'm going to be distinguishing between what I will be calling a cumulative classifier. So in this case, I'll train a classifier on just data from the first time bin, then the first 2 time bins, first 3 time bins, first 4 time bins, first 5 time bins, and then the entire period. And so we give that classifier cumulatively more and more features on which to make that classification. And we'd expect performance of this classifier to increase as we give it additional features, because at worst any additional time bin won't add anything to the decision, but at best there will be some extra information that the classifier then can use to make that distinction. So it should improve performance. And I'll be contrasting performance of that classifier with what I'll be calling an individual classifier. That's a classifier that's trained on only individual time bins, so only on the first, only on the second, only on the third, fourth, fifth, or sixth time bin. And so this will allow us then to distinguish to what extent there's different types of information available at different time bins. So you could imagine that maybe if you have a classifier that's trained on only the last time bin and contrast this with the classifier that's trained on all the time bins, then if there's some different kind of signal that's online earlier but not later, then the classifier that's able to take advantage of the entire recognition period should outperform the classifier that's only trained on the last time bin, because it has some different kind of information that provides independent evidence. Whereas if we think of this as just an evidence accumulation type process where we just keep adding to what we know at each time point, then maybe the neural signal at this time point reflects everything that we've learned at previous time points, and then adding previous time points will not add anything to our classification ability. Yeah.
Why did you define 6 time bin?
Right. So it's an arbitrary decision. You could have used 5 or 7 or 10. I mean, if they're too small, there's a bit of a trade-off. You don't want to make them too small, because especially if you're looking at lower frequencies, it's not really meaningful to talk about power in like 2 hertz if you have 5 millisecond time window, right? And you want to make them long enough that you can fit in quite a number of them, so you can actually look at the dynamics, so you don't just split the trial into maybe 2 bins or 3 bins, right? And 6 is a nice number because it's divisible by 2 and by 3, rather than just even, for example. Yeah. Okay, but I would expect, and as I said, I'll show an alternative way to analyze the data that uses a different approach, and you'd expect those choices not to make a qualitative difference as long as you're using reasonable parameters, and okay. All right, so this is the plot that shows AUC as a function of time for the cumulative time bin. So this is the area under the curve that we get if we just give it the first time bin, and then if we add the second time bin, we get a slightly higher area in the curve. Then as we add more and more time bins, the AUC goes up until it reaches just over 0.7 here. This is for the cumulative time bin. And as I mentioned earlier, we want to contrast the performance for this classifier with the classifier that's trained on only individual time bins, one at a time. And I've overlaid this right here. So you can see the performance of the individual classifier here as a solid line, and then here the cumulative classifier as a dashed kind of red line. And you can see they're completely, almost completely overlapping. They're very similar. And in particular, if you look at maybe this last point here, there we have the cumulative classifier has 6 times as many features on which it can base classification, its classification, compared to the individual classifier that only has 1 time bin. Yet performance is almost identical here. And as I said before, if there's really different types of information at earlier time bin that the cumulative classifier in this case would be able to take advantage of, then we would expect performance between those classifiers to diverge. But in fact, they're quite similar. What we can also do, because we have a trial by trial output from the classifier, and we have trial by trial confidence ratings from the human participants, we can actually look directly at correlating classifier output with confidence ratings. And so this is what I'm showing here. So this is now for the individual classifier that's only trained on individual time bins. We take the trial by trial output, so time is on the x-axis, and we correlate that with the confidence ratings. And I'm just showing you here Spearman's rho. That's a non-parametric measure of correlation between classifier output and confidence ratings. You can see that correlation is quite substantial throughout, but it increases as you train the classifier on later and later time points, suggesting that the signal that we're picking up is actually related to kind of the subjective strength of the memory that we're measuring by asking people to rate their confidence. Yeah.
Have you tried the same cumulative approach, but the other way around, like starting with the...
Yeah, I've done that early on in this analysis. I don't have any plots like this, but you get exactly what you'd expect. That you have if you just train it on the last time bin, you get very high performance. If you trained on the last time bin, that's identical to the individual here, so you get that performance. But then if you add more and more earlier time bin, you just have a kind of flat, so it works like you'd expect. Any other questions? Okay. So this is just another kind of nice feature that our confidence ratings and classifier trial by trial classifier output correlate quite strongly. And then several people have raised the issue. Well, what about these 6 time bins and the length of the time bin varying as response times vary? So I've redone the same analysis by just using 100 millisecond time bins. So in this case, the number of time bins varies. Based on the response time, and in fact I've just kind of had to cut off for this plot. I just had to cut off any trials that were too short or too long, and I'm just showing I'm cutting off data from trials that were longer here, and I've removed any trials that were quicker, and I'm just showing you now the data for 100 millisecond time bins that that just filled in whatever response time there was, and you can see again you have very nice overlap, or very strong overlap between individual and cumulative classifiers here, suggesting that lack of divergence between these classifiers that has nothing to do with the specific number of bins that I used, or the fact that they varied in length with the response times. Yeah.
What was the average time of participants' responses?
It's a good question. It's quite variable, both within and cross participants. I want to say maybe 800 millisecond around, but I haven't looked at this in quite a while. So but that's roughly plus minus quite a large error. So I cut off any responses that were faster than 300 milliseconds, and there were very few of those. And I cut off anything that took longer than 3 seconds, and there were also very, very few of those. Okay. All right. So just to summarize this part, we can say here that the EG signal track evidence for recognition decisions, and that that supports a single root model of recognition memory. So earlier I explained that oftentimes people try to distinguish theories of recognition memory into single and dual process models of recognition memory, with the idea being that for single process you just have a unitary measure of memory strength, whereas for dual process models you take into account different types of familiarity and recollection signals. I don't think this data necessarily speaks to how many different types of evidence there is, but it does suggest that whatever evidence is available, it gets combined into a unitary evidence signal. And so that's why I'm talking about a single root model here. So even if you have different recollection and familiarity signals, those seem to be combined into a unitary evidence signal here that then is used to make the recognition decision. And you could imagine lots of other types of signals that might also contribute to this. So it's rather than having different types of recognition responses based on different types of signals, this suggests that there's a single root to these recognition decisions. And this is work that's came out earlier this year in JEP LMC. So if you'd like to read this, it's available on my website and right here. So I'll encourage you to check that out. And I'm going to...
One quick question.
Yeah.
The single root is based on the fact that you see that there's no difference by just taking these 100 millisecond bins, or basically looking at the last 100 millisecond bins.
Well, so the idea is that at any time point that we look at, if you look at that we have if you just look at individual time bins, that neural activity at that time point incorporates all the information that we have previously, right? So,
but this is across all electrodes and across all frequency bands.
Yes.
So if you broke this down in terms of, say, assuming different routes would combine information through multiplexing different frequencies. So alpha would be related more in one type of memory, episodic maybe would have some more theta activity, and some alpha would be more for just an event happening potentially primarily in different locations.
Right.
So if you run the same analysis with different frequencies and separately for different maybe ROIs, would you expect to see the same thing?
Well, so I mean, I think, right. So that's why I think that's a very good point, and that's why I'm not arguing that there's no such thing as maybe an early familiarity signal and a later recollection signal, and you might figure out some ways to just you look at specific time points or specific frequencies to particularly hone in on those types of signals. But the point here is that even if you look at if there's an early familiarity signal, even if you look at later brain activity, we can still find whatever that tells us about the target Lewis status. It's still there in the EEG activity, right? So it's not the case that what we're measuring here is different types of signals that become available and are not at different times and are just gone. It's more like when we look at all the brain activity that we can measure here, that it's more akin to what you think of if you think of like evidence accumulation, where you add at any time point, you add to what you already know about the target Lewis status, and then at any time point, all information that you've gathered from whatever sources is available in the signal. And maybe an additional caveat to this is that in this experiment, we just ask people to make old new decisions, whereas oftentimes when people try to distinguish, say, recollection versus familiarity signals, they specifically ask them for, say, remember no judgments, where you have to pay attention to am I saying old to this item because I actually remember studying this item, or just because it feels like an item that I probably studied, right? And so if you change the task in that way, where you actually ask people to differentiate between those different types of signals, maybe that would change what we are able to decode at the neural level as well. That's an open question. But usually the conclusion from these types of studies is that there are what we're measuring. If you think back to the earlier contrast that I showed you, where there's kind of this rich dynamic with an early signal that looked quite different from the late signal. People often talk about this as if they're different kinds of signal, they come online at different times, and correspond to these different ways you could make a recognition decision. You could make a recognition decision just by feeling a sense of familiarity, or just by remembering, this is a word that I studied because I remembered, I associate some other word with it when I studied it. But instead, what seems to be the case is whatever information we get at any time point, gets accumulated into a unitary evidence signal. Okay.
Maybe just one last quick
Yeah.
question, just so I make sure I understand. So your classifier, do you oblige it to use all the features you give it, or do you let it choose the best? So in other words, is there a feature selection that is
So
because if you oblige it, it's not the same thing. You might be cancelling. You might get a worse performance, and it might just shoot down just because you try to use all the features you gave it.
So it's free to put whatever weight it wants to each feature. I think it's not a feature selection in the sense that features can drop off completely, but the weight on any particular feature can go arbitrarily low.
What's your classifier?
This is a support vector classifier with a radial basis function kernel, so it allows us to fit a nonlinear partition surface here. But it's a regularized, so it's penalized for larger weights. So there's an incentive to reduce the weights on particular features, and really only features that contribute to the classification should receive large weights in this classifier. Any other question? All right. So right, and so this, and I think one reason why I like this result or this interpretation in terms of single root to recognition memory, that really it links recognition decisions to other models for decisions under uncertainty that generally assume a unitary evidence signal. So if you look at, for example, perceptual decision-making tasks, you have two types of stimulus classes, two types of responses. It's at a high level. It's a very similar type of framework, and there usually the assumption is that you just have some global kind of measure of evidence for the different response classes that you accumulate over time, and then make a decision based on that unitary evidence signal. So it kind of provides this link between recognition decisions and other types of decisions that are quite similar. Okay. All right. So I'm going to try to quickly give you an overview of some other work I've done that uses a similar type of approach to ask a very different type of question. So I'm going to just return back to the slide that I showed you at the beginning, and we've just now kind of focused on what happens. How do we match like a probe item to what what we've stored about it in the recognition memory task. And now we're looking at a free recall task that's much less constrained and where we can kind of disentangle encoding and retrieval processes. So specifically in this type of task, I'm interested in interactions between semantic memory, so what we know about the world, and episodic memory, where I ask people what to freely recall items they've just studied in a prior list. And in this kind of task, what we do is we have a study list, just give people words to study. Then we have a distracted task where they just have to solve some math equations, and then they have a period where they just get to freely recall however many words they can remember having studied. And in those types of tasks, oftentimes people just sample the words from a large word pool and just generate lists of random words. So you might have a bunch of words like this that don't have any particular structure. They're just kind of random samples from a large word pool. But we can also induce a rich semantic structure into the word list. So in the case of this particular experiment, we have 12 items per list. And these items come from one of 3 different categories, and these categories vary across lists. But within any list, there's only 3 different categories, 4 exemplars per category. And so there's this rich structure where we say we have shirt, jacket, pants, underwear. So those are 4 examples of clothing. And then we have table, shelf, cabinet, bed, 4 items of furniture, and then maybe here rain, hurricane, fog and lightning, 4 examples of weather patterns, for example. And of course, in the actual experiment, these are not shown color-coded. I'm just color-coding them here for your benefit, so you can see the semantic structure of this list. And so what happens in this kind of task, when you have this semantic structure, that profoundly affects how people recall these items. So if you think of your ability to recall what you've just studied as indexing your episodic memory, then your knowledge of the world or the semantic structure in this list really strongly affects how you do this task. And the question is, how did that happen? You can think of, for example, in this you can imagine yourself as being maybe a participant in this experiment, and when you're aware that there's this rich semantic structure, maybe during encoding you're focusing on what makes furniture items different from weather patterns, for example, or maybe what makes things in one category similar to one another and different from one another. But you could also think during retrieval, for example, when okay, I remember studying furniture, I remember studying weather patterns, to use those as retrieval cues and guide your retrieval based on that knowledge, and that could also affect effective
structure. Yeah. Do you also mean it's just categories that are available, or are they also presented that way, like two of each? So does the structure give you the fact that you have 2 of the same category each time?
Yes.
Or do you mean just the presence of categories?
So it was always the case in this experiment that we had 12 item lists with 3 different categories, so 4 items per category, and they were always presented in this setting where we have 2 items from one category, 2 items from the next, 2 items from the third category, and then again 2 items from each of these categories. So before I show you any of this, I'll show you what happens when you present this semantic structure. So the first thing you can notice is that performance is a lot better for categorized lists than unrelated lists. So what I'm showing you here is serial position on the x-axis, probability of recall on the y-axis, and if you compare categorized lists to unrelated lists, see that for every serial position, and this is just the difference between those curves here, for every serial position, that difference is positive, so the probability of recall is higher for categorized lists than for unrelated lists. What you can also do is you can measure clustering in these lists, so you can think of, for example, when you recall one item and then you recall another item, is that second item from the same category or a different category? And we can compare this across list types by matching categorized lists to unrelated lists and just calculating the same index for unrelated lists, assuming the category structure of the categorized list, and that's what I'm showing you here. So this is what's called adjusted ratio of clustering. It varies between, well, it could actually be negative, but the maximum value is 1, and this would be complete. You only recall one item from. If there's any item from one category left to recall, you recall it after another item from the same category. You never switch categories when you don't have to. That would be a value of 1 here. And 0 would just be random. You don't really take any category structure into account. And you can see that when you have this categorized list, you're substantially more likely to actually recall items from one category after you've recalled an item from a different category. And when you look at inter-recall time, so this is the time it takes from one recall to the next recall, people in categorized lists are actually a lot faster going from one item in one category to another item from the same category than they are when they switch between category types. So this is the response time here is slower when you go from, say, furniture to weather pattern than when you go from one furniture item to the next furniture item. So those are some very strong characteristics of what happens when you impose this type of semantic structure in the study list. And this clustering seems to be related to the overall recall performance, because this is all within type of comparison for every participant did both categorized and unrelated lists, and so we can actually subtract the kind of the adjusted ratio of clustering for categorized and unrelated list and the probability of recall for categorized and unrelated list. When we plot those differences against each other, you can see that people who cluster more also recall more. So we have this kind of nice positive relationship that suggests that these two things are related. And so the question is, what's going on? Why does the semantic structure have these effects? And to answer this question, I'm going to be using a similar type of approach that I've described earlier, but in this case we are actually dealing with neurosurgery patients. So anyone who's a little bit squeamish, the next slide has a picture of an exposed brain. So just to give you a little warning, heads up, if you don't like to see this, maybe look down. So this is this is kind of top-down view on some one of these patients during surgery. We don't test during surgery. This is just to give you an idea what how we're recording this type of data. So this is an exposed skull, and we have a grid of electrodes just on the cortical surface here. We also have some electrodes that penetrate into the brain. So these are depth electrodes where we can record from more internal structures. And so for each patient, the patient gets whatever electrodes the medical team decides are necessary for the diagnosis, and we just then come in when they're all kind of bandaged up and have the kind of wires coming out of the head, and then spend like a week or two usually in the hospital waiting for seizures. The idea is that if you have this really severe epilepsy that's not effectively treated with drugs, sometimes the last resort is to resect the part of the brain that's the focus of the seizure, and in cases where the medical team is not quite sure where the focus of the seizure is, participants get these intracranial electrodes implanted, and then just spend some time in the hospital waiting for seizures. And then the medical team can triangulate the focus of the seizure from the recordings at these different electrodes. And during times when they don't have seizures and just sit in the hospital waiting for them, we can come in with our experiments and record from those electrodes while these patients participate in these studies. And then when they're all done and the electrodes get explanted, you kind of get really scary looking scars like this, but hopefully without any more seizures. All right. So and one of the challenges in this type of research is that the coverage of electrodes and the types of electrodes, number of electrodes, varies widely from person to person, just strictly based on medical criteria. So in this study we had 69 patients, and this is just to give you an overview of like different regions, how many electrodes we had on the right, left, on both sides, just to give you an idea that the coverage was quite variable in different parts of the brain. And we can make we can look at univariate contrast during encoding and retrieval periods. So this is what we're doing here is we're looking at brain activity across these electrodes while participants are studying individual items, and also while participants are retrieving items. And so what we look at the study period is we're looking at items that people study that are subsequently recalled, and we compare that with items that people are studying that are not subsequently recalled. So this and here have different regions of interest, power and different frequencies. So the red squares correspond to higher power in that particular frequency, in electrodes in that particular region of interest for subsequent recalled items as you look at them during encoding compared to not subsequently recalled items, and blue squares correspond to lower power at that particular region of interest, that particular frequency for subsequent recalled items compared to not subsequently recalled items. And for retrieval, we do something similar. We look at periods just before successful retrieval in the retrieval period, and we compare that to matched periods during the retrieval time that aren't followed by a successful retrieval. And we can do a similar type of contrast, and I'm showing this here. This is both for the unrelated list here. Again, here, red squares correspond to higher power in that region of interest at that particular frequency for successful retrieval compared to unsuccessful or failure to retrieve, and blue squares is lower power at that particular frequency in that particular region of interest for periods that led to successful retrieval compared to failure to retrieve. And you can see in both of these cases we have higher power and higher frequencies and lower power in lower frequencies corresponding with successful memory. And when we compare this with the same contrast for categorized lists, qualitatively it looks quite similar. You can try to look and nitpick about different squares being on and off, but this is also a threshold statistical map. So if you change this threshold, the particular pattern will change. It's really hard to know what to make of this. There's not an obvious difference, and certainly there's not a case where you say, oh, it's definitely something that's happening in encoding, or definitely something that's happening in retrieval that's causing this difference between unrelated and categorized lists. Certainly, if you kind of squint a bit, they look all like kind of similar-ish. I think you would agree, right? So and here. I think it's another case where this power of using these classification methods can help us get a richer image of what's happening in the brain activity and the type of information that's available in the neural signals.
So the contrast is between successfully retrieved and errors. Both for the and for the encoding? So in the encoding we look at brain activity during the presentation of an item in a study list. And we compare items that later are subsequently recalled and items that are not subsequently recalled. Right. In the retrieval period, we look at periods during the retrieval time, just before people make a successful retrieval. And we match times during the retrieval period that aren't followed by a successful retrieval. That's a contrast in the retrieval period. Okay? Okay. And so in particular, what's usually the case when these types of classifiers is trained, that we train, let's say, on a categorized list, maybe during encoding or retrieval or whatever, and then test also on the same type of list. And we do the same thing for unrelated. We train on unrelated lists and test on unrelated lists. And I'm going to be calling this a decoding approach. But to the extent that neural activity generalizes across list type, we should be able to train on categorized lists and maybe test on unrelated lists, or train on unrelated lists and test on categorized lists. I'm going to be calling this a cross-decoding approach, right? So logic is here, to the extent that neural signals are shared across list types, performance of decoding and cross-decoding classifiers should generalize. To the extent that they're not shared, performance between these types of classifiers should diverge, okay? And so what I'm showing you here, this is a bit of a complex figure that I'm going to walk you through quickly here. So I'm showing you a bunch of different ROC functions. This is the same type of functions that I presented earlier in the SCULP EEG study. We have the false alarm rate here, hit rate here. This is just for the classifier performance here. And the solid lines are decoding, the ROC functions for the decoding classifiers. The dashed lines are for the cross-decoding classifiers. And these little panels on the side of each of these ROC panels, it just shows the difference in area under the ROC function. So for example, you can see that those ROC functions here in this panel almost completely overlap, and so the difference in area is close to 0, and that's what's shown here. On the top we have these functions for categorized lists,
on the bottom for unrelated lists. Left column is encoding, right column is retrieval. And you can see a few things here. First of all, is that there's considerable overlap in the ROC functions, or the areas of the ROC functions. So it's always the case in all of these cases that cross-decoding performance is above chance. So that suggests that there's a significant shared neural signal between these list types. But there's also some divergence. There's a little bit divergence here, but quite substantial divergence between these functions here during the retrieval period. Suggesting that here, in particular during retrieval, the neural signal differentiates between lists of different semantic structure. What I won't have time to show you, but what I've also done here is I've used a similar decoding and cross-decoding approach for recalled items, where we can predict whether those recalled items are recalled within a semantic cluster. So, for a recalled item, is this item going to be recalled right after another item from the same category or another item from the different category? And we can also do this for temporal clustering. You can see whether an item is recalled right after an item that was presented nearby in the study list, or an item that's further away in the study list. And if you do this, do the same type of analysis, but instead of predicting successful recall, you predict subsequent clustering. You again find only in this this combination of retrieval and categorized, in this panel, do you find this divergence between decoding and cross-decoding performance, suggesting that retrieval processes in particular are driving these adaptations to the semantic structure of the list. So let me summarize very quickly. Encoding processes largely generalized across lists with varying semantic structure, and this is, as I mentioned earlier, just obvious from the strong cross-decoding performance. But retrieval processes in particular adapt to task demands even when these are apparent at encoding. So our semantic structure of the list was very evident. It was always the same setup in the represented block. So it was very, very clear that lists were semantically related. So during encoding, that information was available. Yet it seems to be that at retrieval is where we see the most obvious differentiation between these decoding and cross-decoding classifiers. Yeah.
And just to be sure that again it's across all regions and all frequencies.
Yes, yes. Well, and in this case, there was some more variability in where we, in terms of regions, because every participant had different regions. So, I think I'm already out of time, so I'm just gonna end it here. And thank you.
Okay, maybe time for one or two quick questions, if you have any. Maybe I had one quick question related to the how you draw a conclusion based. So the discussion slide you just that was your final conclusion about the second one, which comes from the comparison of the cross decoding.
That's right. Yeah. So
maybe you can walk us on it again. How do you move from that to concluding this?
Right. So. Well, so the bit of apparent at encoding is just something that is due to the experimental design, right? At encoding, it was very clear that there was a semantic structure. That's not something that took any effort really to figure out. And the main reason for this is that there's really this is here during retrieval. Here, this is the biggest divergence between decoding and cross-decoding. There's a little bit here, but it's much smaller. And when we look at the predicting subsequent clustering, we don't see any divergence here, but we do see divergence here. So that implicates, that particularly implicates retrieval processes in driving this clustering and the differences in recall performance.
But you have differences in reaction times, potentially, between the two types of tasks. Do you?
What do you mean by reaction times in this task?
For example, because we're not getting into the details of how you analyze for your machine learning classifier, but you're choosing frequency bins and you're computing the power.
Right.
In windows, and these windows are going to be probably aligned to the probe.
There's no probe in the free. It's a free recall task here, right? So we just have.
There's a time zero on which you're going to align to compute your features. for
Yes.
the classifier on retrieval.
Yes.
And my question is, on those windows, how confident are we that the dynamics are similar across the two tasks? Because that might be an issue. Maybe I'm just.
When you say, you mean across the two periods, you mean across encoding and retrieval, or?
No, across the category when you're doing the cross.
Oh, but we are always using the same thing. So when I train on the categorized, so I'll train on the categorized list, and I'm using the same training features to then either test or predict on categorized lists or on unrelated lists. So the features for the classifier is identical in both of these cases, just what I'm testing it on, and likewise, the other way around. So and I'm doing it in both directions. Yeah. Any other questions?
No questions? Okay, if no questions, so we'll thank our speaker once again, and he'll be around for those of you who want to come and talk.
Yeah. Thank you.